Welcome to Further Solutions Academy. Please do well to subscribe to our YouTube channel. Do well to share our videos and subscribe to our YouTube channel at Further Solutions Academy. And also, if you have any questions or you have any comments, you can also comment on the YouTube page. And if you have any contributions or comments that you want to reach out to us, you can reach out to us on this number. Yes, so please do well to reach out to us when you need to. Oh, sorry, it is 9:05. Okay, so today we would be discussing on chemistry, and the aspect of chemistry we'll be talking about are the reactions of benzenes. The reaction of benzene. Before we go into the reactions of benzene, you should know that benzene is an aromatic compound, and is a specific aromatic compound because it is quite unsaturated, but unlike other unsaturated hydrocarbon, benzene does not really allow for addition reactions except at adverse or very critical conditions, which it supports hydrogenation and so on and so forth. But the major reactions that benzene undergo are known as electrophilic aromatic substitution reaction. Electrophilic aromatic substitution reaction. Substitution reaction. So these are the major reactions that benzene undergoes, and we have the general mechanism of these reactions, and we also have specific type of electrophiles. So if you look into this, we know that, okay, fine, when we are talking about aromatic, we are talking about the ring-like structure of benzene. Then also when we talk about electrophilic, from the word electrophile, which means it is electron loving. Then substitution reaction. Now this is a major point that we need to look at. Benzene allows more substitution reaction than addition reaction. Reason being the fact that it will not allow anything to distort the bonds or the pi electrons in the ring. So it allows for substitution reaction where something is being substituted for the hydrogen, or an hydrogen is being replaced for a particular electrophile. Like I said, an electrophile is an electron loving group that is attached to the benzene compound. So we have different types, but let's first talk about the general mechanism. The general mechanism of these reactions. There are three different steps of the general mechanism. The first one, please do not forget, is the generation of the electrophile. The generation of the electrophile, very, very important. Then the second one, this is with respect to the different kind of electrophiles we'll be talking about, which we'll be doing that in the course of this lesson. The second one is the attack of the electrophilic reagent. The attack of the electrophilic reagent, and the last one is the loss of proton from the benzenium ion. Yes, benzenium ion, loss of proton from the benzenium ion. So these are the common steps that are peculiar to every electrophilic aromatic substitution reaction that you can find in benzene. So there are about 5 different types of reactions that benzene undergo. We may be able to cover some for this lesson, and if we are unable to, in our next lesson we would finish it up and we'll go on to the next thing that we have to talk about. So first, we have different types. Like I said, the first one is nitration reaction. Nitration substitution. There's no need for the reaction. Then after the nitration, we have the sulphonation. We also have the halogenation, and we have the Friedel. That's Friedel alkylation and acylation, which is 4 and 5. 1, 2, 3, 4, 5. Yes, these are the 5 major reactions of benzene that we have for electrophilic aromatic substitution. And we will be starting with nitration reaction first. Like I said, when you are asked or you want to describe the reaction of benzene, it is expedient that you derive or show how you are generating your electrophilic reagent. And the first thing is in the generation of the nitronium ion of the benzene. The generation involves 2 different acids, which is the nitric acid and the sulfuric acid, at a high temperature of about 55 to 60 degrees Celsius. So it is being heated. Then the nitrating agent, after being heated, forms the nitronium ion. So this is the equation for the generation of the nitronium ion. We have HNO3, which is nitric acid, plus H2SO4, the sulfuric acid. We have 2 moles of this. So we have okay, yes. So this, I think we have 2 here. Okay, which makes it balanced. Yes, which makes it balanced. So we have this to be our generation, the generating of the nitronium ion, and this is our electrophilic reagent. The nitronium ion is this among all we have gotten. So the second step is this: we attack the benzene ring. So we have a benzene ring. We have a benzene ring of this kind. Okay. Now, because benzene ring is rich in pi electrons, so one of the pi electrons attacks this electrophilic reagent, thereby creating a cationic resonance stabilized benzenium ion or compound. Now, what do I mean by that? So we have something like this, and moreover, this is a slow step in the formation of this compound, so of nitrobenzene. So this is a slow step, and because this is slow, that means this attacks this. The electrons here attack the electrophilic reagent, and after attacking the electrophilic reagent, like I said, there is a formation of a resonance stabilized. There's a formation of a resonance stabilized benzenium ion. So this actually can have different canonical structures, where we can have this bond moving to this, and we have something like this. Yes, this bond moving here. So we are left with excuse me. So we have this, say this is coming right down here. Okay, let's draw the structure over again, so we can do that from the onset. I think there's a mix up there. Okay, so if we have this, let's say we have this as our plus our nitrating reagent. Like I said, this attacks the nitrating reagent, and this is a slow step. So the next thing we have, because of this happens, this place becomes, there's a positive sign on this part. There's a positive sign on this part, and our bond is already with our NO2, then the hydrogen which was there originally. Our hydrogen which was there originally. Okay, good. So when we have this is as a result of this carbon being joined to just 3 different atoms, which is the hydrogen, this carbon, and this carbon. So it is a bit deficient, so it has a positive sign. And this positive sign, like I said, is resonance stabilized. Like I said, is resonance stabilized. So because it is resonance stabilized, due to resonance effect, the bonds can oscillate, having different canonical structures. Where we have something like this oscillating to this, then we have something like this. Forgive my structures for benzene. Okay, then we have our charge here because this bond is moving towards this way. So we have our NO2 and hydrogen. Then we can also have another structure, which we have this coming to this place. Then we have our positive charge here. This bond has collapsed here. Then we have NO2 and our hydrogen. Sorry, forgive me for that. Okay. All right. So we have this. Then we can have the hybrid structure of this, where we have something like this to show that the positive charge is oscillating around it. To show that the positive charge is oscillating around it. So all of this that we have, let me say, all of this that we have is the resonance stabilized structures, and this is the hybrid structure of the oscillations that we can see of the positive charge. Then the next thing, like I said, is the loss of proton, because this proton needs to be lost for this compound to be balanced. So how do we do that? We introduce, remember that part of our nitrating reagent, we have something of this sort. Something of this sort. So this is able to create an acidic medium that can abstract this hydrogen. So what do we say in the last point? We have something like this. Let me just pick one of the resonance structure for this. So let's just say I'm picking this, where we have NO2 and our hydrogen. So in the presence of this can abstract hydrogen to form our acid. So let's have this plus 2HSO4 plus. This can abstract the hydrogen, so we are left with, when it abstracts the hydrogen, this bond collapses back on this. So if hydrogen leaves not as a atom but as a proton, so when hydrogen leaves as a proton, we are left with our formation of nitrobenzene and sulfuric acid. So we have substituted the hydrogen on the benzene ring for the nitronium ion just by this mechanism. And the good part of this mechanism is that it follows the same process for all other kinds of reaction. So let's just go to the next one. Let's say we are talking about sulphonation reaction. Sulphonation reaction. Sorry for the break earlier. So the second reaction is the sulphonation. Let's just leave it as sulphonation. Here we are introducing a sulfonic acid, which is the sulfonic acid group SO3H group. We are introducing this to the benzene ring. So this is our incoming electrophile. So, but how is this formed? This can be formed in the presence of oleum or in the presence of fuming hydrochloric acid, where we have 2 moles of, we are trying to generate the electrophile, so we have 2 moles of H2SO4 to give us HSO3 plus H3O plus HSO4. I hope this is right. Okay. If I'm not mistaken, I think this should be right then. I think this should be right. Then also it should be balanced. Should be balanced. If it is not, then probably we can look into it together. So looking about the balancing, okay, why don't we try the combination of SO3 for just like we are trying to derive oleum. So we have SO3 plus H2SO4. I think this should give us SO3H plus HSO4 minus. Okay, I think this is right. Okay, good. So we've had our electrophile that we want to attach. So having our electrophile, the next step, like we said, is the attacking of the electrophile to the benzene group. So we have the same similar process that we followed earlier. So we have something like this. Plus SO3H plus. So this attack this, and like we said, this is a slow step. Oh, I forgot to mention, the removal of the proton step is the fast step. The loss of proton step in the third step is the fastest one. So here we have our slow step where this attacks this, and we have something of this sort. Our positive sign here because carbon is joined to just 3 atoms. Then we have SO3H and our hydrogen. Now this can actually undergo the resonance structures just like we have done earlier, but we can also have the hybrid structure to show that the positive sign is resonating round. So we have SO3H and we also have our hydrogen. Now this hydrogen needs to be lost. How can it be lost? Most likely this comes to abstract this hydrogen on the third step. So we have something of this sort. Let's just say I'm picking one of the resonance structures plus HSO4 minus. So this takes hydrogen as a proton, and we are left with our sulfonated benzene plus sulfuric acid. So this is just the simple. This could have been elaborated just like we did for the nitration, but rather still, because of time, it is better we have the hybrid resonance structure to explain that. Then the third one we'll be going to is the halogenation. The halogenation of benzene. You could use different halogen. You could use chlorine, you could use bromine, but most likely let's just use bromine for this. So the third one is the halogenation. When you hear halogenation, it means halogen is attacking benzene. But this cannot just happen except in the presence of a Lewis acid, where the incoming halogen is acting like a Lewis base. So let's say we are using something like a bromine. We are trying to derive the electrophile. So we have bromine plus FeBr2, FeBr3. Yes, this is acting like a Lewis acid. So we have this to give us bromine plus FeBr4 minus. How do we get this? Let me just briefly explain. You know, we have bromine plus FeBr3. So this gives us just one bromine as a positive side. Then this other attaches itself with this, making or thereby forming a kind of a molecular complex. Here, a molecular complex or an acid-base complex of this. This is actually a complex. This is actually a complex. So that is how it happens. And we have generated our electrophile. I believe you know our electrophile in this. So this is the electrophile that we are dealing with. And we are attacking this to the benzene ring. The same process all over again, the same mechanism. So we have something like this. Plus Br plus, okay, this attacks this. Like we said, this is a slow step also. We have this, our positive sign. We have bromine and we have the hydrogen. Just like we did earlier, we could have our resonance stabilized hybrid, our hybrid, then we have the Br and we have the hydrogen. But hydrogen needs to be lost so the formation can be complete. So how is hydrogen being lost? From this complex, remember that we have 4 molecules of bromine atom. So we could have said that we have something like this. Where one of the bromine atom could still attach itself to abstracting this hydrogen as a proton. So in the presence of this kind of complex, we can have something like this. Let's just say I'm picking one of this. So this is able to abstract hydrogen as a proton, then this bond collapses here. So in other words, we have something of this kind. Our bromine is formed and our benzene ring is returned to normal because this bond collapses here, and we have our HBr, which is this hydrogen with this bromine, and you realize that we have our ion FeBr3 all over again. So sometimes FeBr3 is just acting as a catalyst in this reaction. So that is how halogenation is being done. So the next thing we will be talking about is the Friedel acylation and acylation. The Friedel acylation and acylation. So let's just talk about the Friedel acylation briefly. Actually, this is the name, a compound name of 2 different chemists. We have Friedel and Kraft coming together, making this up. So they are making acylation process as a reaction of benzene. And how is this possible? In Friedel acylation, the key word there is the alkyl. So we are trying to attach an alkyl to a benzene, but this is done in the presence of an alkyl halide. Let me just use an example. Let's say we are having and when we talk about alkyl halide, something like RX, where R is an alkyl. It could be ethyl chloride, it could be ethyl bromide, propyl iodide, and so on and so forth. So we have our alkyl halide here, and we want to generate the complex, but this is only done in the presence of Lewis acid, most likely aluminium chloride as Lewis acid. So let's say we have RCl plus AlCl3, where this is what? Our Lewis acid. Then we also have this generating a carbocation. A carbocation is being produced from the alkyl. After a carbocation is being produced, we also have a molecular complex here, which is AlCl4 minus. So we have something like this. There's a way to explain this in an elaborate form, but because of time, I would be leaving us with this. So this becomes our electrophile that we need to attach to the benzene ring. So attaching this to the benzene ring, it still follows the same process, which we have our benzene ring, of this sort, so plus our R. Now, just because I want to, for proper understanding, let's say I am changing this R to be C2H5. So this becomes what? C2H5. So we have something of this sort, and this becomes C2H5 carbocation. So the same process all over again. So we have this C2H5, then our hydrogen. This follows the same resonance form as we have done earlier, and we could have the resonance stabilized form. But this hydrogen needs to live as a proton so that this compound could be balanced. And how is that done? It is done through this complex. Remember, like we did in the last one on the halogenation, we have a chlorine atom here that is possible to abstract the hydrogen, thereby forming hydrochloric acid. So how do we do that? Like I said earlier, we have Al, Cl, 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 and Cl. So this complex, we have a chlorine atom that can actually abstract this hydrogen atom, and we have something of this sort, C2H5. Okay, it will be better for me to put my hydrogen on this side. So we have hydrogen, C2H5, then okay, so one of these chlorine picks up the hydrogen. After picking up the hydrogen, we have the formation of our acylated benzene. Because why? When it picks up the hydrogen, the bond drops. So when this bond collapses here, we have our acylated benzene of C2H5 plus HCl, hydrochloric acid, and we have our lowest acid back again, which means it's acting mainly as a catalyst. So we have AlCl3, and these are the products of Friedel acylation. Nevertheless, there are some limitations to the use of Friedel acylation. There are some limitations to the use of this. The first limitation is that if there is the presence of an electron withdrawing group on the benzene ring, it does not allow for this alkyl to attach itself. Example of electron withdrawing group, we have something of this sort, COR. Okay, we also have CHO. Yes, example. So if this was present on the benzene ring, it will not allow the incoming alkyl. Another thing is that one of the limitations again for Friedel acylation is that there's a tendency for rearrangement to occur. There's a tendency for rearrangement to occur. For instance, if I'm using an isobutyl, or isobutyl chloride, something like an isobutyl chloride, you realize that there will be a rearrangement. Let's say I have something like this. Isobutyl chloride. Okay, something of this sort. Okay, while this is leaving, we'll be having something of this sort. There will be a kind of rearrangement that is occurring to this compound. Because why? The carbon or the carbocation tends to be more stabilized when it is at a tertiary position rather than when it's at a secondary position. So every carbon at the secondary position tends to rearrange itself in a way, so you end up having a product that you may not desire. And another thing that happens with Friedel acylation also is that aryl halide and vinyl halide cannot participate in this because of the difficulty in giving a carbocation. So another thing is polyacylation can actually occur. Polyacylation can occur after attaching an alkyl. The process continues because why? The activated alkyl group on the benzene ring makes it more activated, makes it more reactive. So it tends to continue, and the only way to stop that is by adding excess benzene. So let's go to Friedel acylation. Friedel acylation, which is the last one. This is how this is formed, is ROCl plus, in the presence of Lewis acid also. In the presence of Lewis acid, we have RCO, which is our acylium ion. Our acylium ion is formed with the complex also. So this acylium ion is what is attached to our benzene ring. And when that happens, we are just the same process all over again. We are left with this COR and H. Yes. So we are left with this COR and H. Then the proton needs to also leave the same process, just like we have done earlier. This abstracts the proton from this, and we are left with when that happens, this bond collapses. When this bond collapses, they are left with COR, where R can be any alkyl. So for instance, I can prefer to use CH3. I can prefer to use ethanonyl chloride, where I'm having our R to represent a particular alkyl, and that is all on Friedel acylation. So these summarily are the reactions that benzene undergo, and they are known as the electrophilic aromatic substitution of benzene. If you like our video, please share with your friends and subscribe to our YouTube channel once again on Further Solutions Academy.